Hello everybody and good day. Today I want to introduce you to sparse matrix storage schemes. Before we start, let's consider the following example. So assume a 10 by 10 matrix is given, stored in a file, and you want to apply the power method. Let's say you want to compute the matrix vector product of the given matrix with an random vector. So how could a first program tackling this problem look like? What happens if a matrix is given which is 100,000 times 100,000? Which runtime you would expect and which storage requirements will be? As a third task, assume a matrix 10,000 by 10,000 is given, or 100,000 by 100,000, but only 10 non-zero elements per row are given. So matrix 100,000 times 100,000 probably will be too huge to store in your home laptop. But if the matrix has only a fixed number of elements per row and the number is small, the storage would be possible. But how would you realize the matrix vector multiplication? And that would be the topic of today's lecture. And the question is if there is the most efficient or only one way how to realize the implementation, or what we have to consider. Does it depend on the computer, the computing device, if it's a graphical programming unit, or is it a parallel computer? Is this parallelization only for a few computing units, 4, 10, or 10,000, which makes it a difference for the matrix. So we talk about sparse matrices if we have only a few non-zero elements and we can take advantage of the structure of the matrix. Large and sparse matrices typically arise when you have the web informational retrieval. Think about you have a search on the Google machine or a Google search. There could be algorithms for this page ranking, which rely on the eigenvector computation. We'll talk about sparse matrices when matrices have only a few non-zero elements, and we can take advantage of having special formats. If you have only matrices which are less than, let's say, 100, 1,000, in general you will have no advantage. The overhead of special storing the matrices, there will be no benefit. But if you have large and sparse matrices, which are typically occur, let's say, in the web information retrieval, let's say you have doing some Google search, you have identified a few web pages where the expression, the token you're looking for is included. So you will end up with, let's say, 10,000 web pages where would you like for high performance computing as an expression. But how you rank these web pages, and there is one very good algorithm, PageRank algorithm, which relies on computing the eigenvector for the largest eigenvalue in magnitude. Or you would like to compute the Fiedler vector, which is more or less the opposite, considering the Laplacian, so matrices, roughly speaking, where the smallest eigenvalue is 0, the row sum is 0, and all off-diagonal elements have the same sign, and the diagonal is just the sum of all the off-diagonal elements per row with a negative sign. So the Fiedler vector is interesting in matrix reordering, as we'll see in graph partitioning, or more applied problems like protein analysis or machine learning. And one focus is also using large sparse matrices occur in the standard discretization of partial differential equations with finite elements, finite difference schemes, or finite volume schemes for solving partial differential equations. So due to the fact that we have a very large number of zero entries, so special schemes are required to store these sparse matrices to take advantage. One key issue is to define data structures for these matrices so that we have an efficient implementation for standard solution methods. So let's say direct or iterative methods. For the iterative methods, mainly the focus on the matrix vector multiplication. For direct methods, there's the thing about the Gauss elimination or Cholesky factorization. You will get fill-in somewhere in the matrix. We'll see that it's not randomly, so there's some structure where the fill-in will occur, and how we can specify the storage scheme also for these matrices. So if we have special schemes to get rid of all these zeros so that we store only the non-zero elements, it makes possible to store very matrices, sparse matrices of very large dimensions. So let's say 1 million or 10 million on your home laptop or computer will be possible. So sometimes zeros are stored, the explicit zeros. We know that there are zeros, but then it may be an advantage to maintain block or symmetric sparsity patterns, for example. In most of the time, the formats we're considering are optimized for space matrix vector multiplication, and at the end of the day, we have to take into account the amount of storage these schemes will need, and if there's nothing, there's no free lunch. So what will be the conversion cost of a given matrix to this specific format? So to discuss the different storage schemes, before we introduce a few terms to quantify the structure of the matrix, not only symmetry, there are more terms we need. So structured and unstructured matrix, if you see the figures below, on the left hand you see a matrix which may arise from the discretization of the Laplacian on unit square, and it's not needed that the sub and super diagonals will have the same entry. So this entry in the upper part have to be the same entry as in the lower part. We only consider if there is a non-zero or a zero entry, so that we need a storage place for these elements. So these structured matrices quite often arise if you apply the finite difference method for solving partial differential equations on simple, more or less rectangular grids. In practice, if you apply the finite element method or the finite volume method on a more complex geometry, you will end up with matrices of this style, of much bigger dimension, but you will see, or more or less have no structure, or even if there would be some structure, it's quite expensive to use this structure. To discuss the structure of sparse matrices is a very good idea to use it by graphs. What is a graph? A graph is a graph G is defined by two sets: a set of vertices, capital V, and a set of edges. And an edge is just the directed edge pointing from a node Vi to a node Vj. So it's given below. So here we have the set of 5 vertices, 1 up to 5, and we also have edges given in the set. So the edge 2 pointing to the vertex itself, 2, or pointing from 2 to 3, given below. And this is nice picture. And from these graph, we can get some, we can apply some necessary theorems. So using these graph, we also introduce the term of adjacency matrix. So the adjacency graph of a sparse matrix is a graph whose n vertices in V represent the n unknowns. So there is an edge from I to j when the element of the matrix Aij is non-zero. The adjacency matrix, of course, is an undirected graph when the matrix pattern is symmetric. So if Aij is non-zero, it implies that also Aj is non-zero, and vice versa. So of course, if the matrix is diagonal, all the unknowns are independent. And if a matrix is dense, so each unknown will depend on all other unknowns. And there will be, if you have a matrix of dimension n, there will be n edges pointing from one node, one vertex to all the other vertices. And sparse matrices lie somewhere between these two terms. Here we see the adjacency matrix of a matrix where for the element Ji, there's also one entry Aij that gives some undirected graph, which is depicted here. And on the right, you see a graph which is directed. Let's say for at least for example, A41 is given here, pointing from 4 to 1, but not from 1 to 4. Reordering. So probably, as you remember from the example in the introduction, with focus on the LU decomposition, it can be very interesting to consider different reordering schemes. What are reorderings? Let's say given matrix, and if we reorder the rows, let's say we have given a permutation pi I1 up to In of the sets 1 up to n. Then we have the matrices A pi asterisk, where we have the permutation of the row indices, or A asterisk pi, which is the permutation of the column index. So we call it symmetric permutation if we permute the rows and the columns with the same permutation. And this is equivalent to relabeling the vertices of the graph without altering the edges. As an example, consider the following linear system of equations: Ax equals b, where A is given. Now we apply the permutation of row and columns with the following permutation: 1, 3, 2, 4. That means we have to swap the second and third row and the second and third column, so that we end up with these matrix. This has also the same solution. How we can take advantage after applying this permutation? Of course, here we see that this matrix has some tridiagonal structure. There exist efficient solution schemes if my matrix would be much larger, and that we gain some benefit of it. As also the reordering with respect to the LU decomposition. On the left, let's say this arrow matrix, which is pointing to the right lower edge. Here we have the node number 9 in the middle, and there are edges pointing to all the other nodes 1 up to 8. The same pattern of the graph is given on the right, where we relabeled the vertices and we end up with this kind of matrix. What is the difference for both matrices? If we compute the L decomposition for the matrix on the left, of course we see that we only have to eliminate the entries in the lower and the lower row and the right column, and we can store the resulting resulting matrices L and U in place, let's say on the storage places where the non-zero element exists already. So there will be no fill-in where we have already zeros. On the other hand, if you try to compute the LU decomposition for the matrix on the right, if you eliminate now, let's say you have to eliminate this entry here, then you subtract this row multiplied with a factor, with a non-vanishing factor. So this will get fill in on this. Then you like to eliminate this part. Then you get fill in on the whole row. And in general, the LU decomposition will end up with dense matrices. Dense in the sense that the matrix L is a lower triangular matrix, but all entries in the lower part are probably non-zero. So that makes sense to find some optimal reordering, so to get rid of, to minimize possible fill-ins. There are different schemes of reordering. Just to mention a few level set orderings. We'll see later that the reverse Cuttle-McKee is one scheme which gives low number, but the problem of finding the best ordering, let's say with minimizing the bandwidth or minimizing the size of the envelope, are NP complete problems. So we rely always to have some approximation of the optimum using some heuristics. Other methods will also be multicolor ordering. We will see it later with a red-black ordering with respect to the Gauss-Seidel method and parallel versions, or with respect to the Cholesky or Gauss decomposition of sparse matrices, the AMD ordering, so the approximal minimal degree ordering. So let's do a small example how to illustrate the ordering effect. Here we do small code where we build a specific matrix. Let's have a look of this matrix. So this given here, and now we apply SPI A, and this is the pattern. So we probably will do it here. Just 4 SPI A, and save this. That was okay. This is the pattern. So if we see later, this is a 4x4 matrix, repeating 4 times, and some super and subdiagonal. This matrix is symmetric, as we know, and therefore we want to count the entries of non-zeros, which is 3L of A, and this number is 40. So let's also do this, figure 1. Then SPI this, and on figure 2 we compute our Cholesky matrix. Cholesky of A usually gives the upper part, but I want to see the lower part, and this gives SPI L. And let's say we will use it as markers. No, SPI L. Running this code gives this fill in. We do it another way. So here we plotted this and we use the spark as a square and the size will be 12. And here we use for SPI the same figure. Hold on SPI, where we use just this as fill-ins and hold off. And what we see is blue are the markers, squares, let's say, here we red, and this will be carbon. So the red ones are the entries of the lower part of the original matrix, and the black dots are fill-ins due to the fact that we computed the Cholesky decomposition, and the black dots, as we see, are all right from the red dots. They're always between the diagonal and this part. Let's do some trick and we compute P, let's say symmetric approximate minimal degree. I have hopefully the right command of A, and we do some LP, should be the Cholesky decomposition applied to A permuted, and again transposed. We do the same figure as before, so figure 2 should be SPI our matrix, and then hold on, we have some LP. We give the entries, the non-zero entries of matrix A, or let's say the lower part of A, including the diagonal, the non-zero entries of our matrix L, and then Z of our permuted matrix LP. So do this one. And here we see figure 2. I'm confused. Okay, not confused. Of course, we have to use also the permuted matrix. Not L, but here P. Okay. The first picture was the original matrix, and we see that we're all possible fill-ins besides the first ones are filled in. If we use a different permutation, we have less fill-ins. Here we fill-in of 27. Here the fill-in is only 18 additional entries we have to store. Of course, it's a very small matrix. We'll go ahead and let's plot it. It's not that nice, but we see that we save half the storage, which is usually without permutation would be used. So that will be the pattern. You see, everything which is possible is filled in, and in the second part there's much smaller fill-in, what we see from the number. That's the number of entries of the decomposed matrix after the decomposition by the Cholesky decomposition. There also we can do other permutations. We can also use dissect. So bisect the graph in a specific way, and if we do this way, it's similar. Here you see the kind of bisection in the upper half is always a little bit less. Probably later we'll come to this kind of ordering, or this is one kind, and we also have this symmetric reverse Cuttle-McKee, as I mentioned before. If we apply this reordering, we see again this different, very small small band. Okay, it's not as good, but we have different focus of this ordering scheme. Before we skip into the big area of storage schemes, what we start with. In order to take the advantage of the large number of zeros, we'll see what is given. Let's say we have a general matrix A, which is an M times N matrix, and Z will be the number of non-zero elements of a matrix A. And also D is the number of bytes required for storing a single matrix. In general, or usually we use D equals 4 for a single precision, or for D equals 8 for double precision real numbers. If we have double precision complex numbers, D equals 16. So under the assumption above of the definition of D, we need an amount for M times N times D byte to store a dense M times N matrix. So the question is, if the Z is lower than M times N, exists there better storage schemes? The question we have in mind is, when we introduce different storage schemes, is it easy to the conversion between different formats, or is it easy to append or deleting matrix coefficients or whole rows or columns? What about the cost of the matrix vector product, depending on the various computer architectures? What about sparse direct solution methods for matrices which have medium size? And also, what is about storage or store and load and display matrices, matrix entries? And this we'll see in the next second part.